where are we and what are what's the science and the engineering taking place to prepare for the future. So before we get started, I'd like to go over a few housekeeping items. So you know how to participate in today's events. At any time during the webinar, you'll have the opportunity to submit questions to today's presenters. Just type your question in the question and answer tab at the bottom of the control panel, and as time allows, the presenters will address as many questions as they can during the Q&A session at the end of their presentation. We will be recording this webinar, and we'll share the recording after the event on the NanoCanada website, nanocanada.com. And that's it for housekeeping items. So it's a great pleasure for me to introduce Dr. Peter Herman, who received his Bachelor's of Engineering degree in 1980 at McMaster University. He then got a master's and PhD degrees studying lasers and diatomic spectroscopy in the physics department at the University of Toronto. And he went for a postdoctoral position at the Institute of Laser Engineering in Osaka University in Japan to study laser plasma physics and X-ray lasers. And he came back to Canada and joined the Department of Electrical and Computer Engineering at the University of Toronto in 1988, where he currently holds a full professor position. Professor Herman directs a very large and collaborative research group that develops and applies laser technology and advanced beam delivery systems to control and harvest laser interactions in new frontiers of 3D nanofabrication. And the mantra of the group is, we begin with light and we end with light devices. So to this end, they're inventing new methods for processing internally inside optical materials that carve out highly compact and functional light wave circuits, microfluidics, optofluidic systems, biophotonic sensors, and smart medical catheters. Goals is about inventing new manufacturing processes and extending optical devices and lab on a chip concepts towards more compact lab on a fiber and lab in a film microsystems. So it's my pleasure to invite Dr. Herman to share with us his talk, Laser Fabrication of Optical Microsystems for Photonics Packaging. Dr. Herman.
All right, I think you can see me now. So good morning, everyone. It's a pleasure to be here and in this topical area. I think this question's been posed for decades. Even when I was a graduate student, I remember chemistry professors talking about molecular electronics when this day would come. And surprisingly, many decades go by and this keeps pushing, and plants are even more expensive. The devices are smaller. It's very unclear now how many more years and not decades will be left here. Now, in my area, as you heard, I'm working with lasers and working more on the packaging aspect, not directly in the silicon chip, but how to facilitate communications there. And so let me start with my slides now. This just I have to do a little gymnastics here to switch screens. And let me get my laser pointer. There we go. All right. So it's great to be here. And like you heard, our mantra here is we start with light, that's laser light, and we work with optical devices. So maybe we can go back to some time to the early days of lasers. And as we're scaling power up and playing with optical materials, one gets, unfortunately, damaged. This is an image from Emin Optics. It's a laser burn hole. Yes?
Excuse me, sorry, your presentation's not up on the screen. You're not sharing it yet.
Oh, indeed. Okay, thank you. I forgot, didn't I? Okay. So let's go back.
We see it now. We see your group photo.
Okay, yes. Okay, so there's my group, and now we can see everything. All right, so in the early days of the laser, this is the kind of damage that would happen, and we can turn this sort of disadvantage into an advantage, particularly if we shorten the pulse duration, and we can actually steer and manipulate how the light is absorbed and the kind of pathways that the light can take. So here's a kind of overview slide of the physics. So we're not even worried so much about processing at a surface as we are in a volume. So we have the ability by putting a focus of light into a material to turn on some kinds of physics. And we have to remember from material interactions, polarization has a scaling with the electric field of light. Then first order gives us absorption and refractive index. Well, glass doesn't absorb, and because it's symmetric, it doesn't even have a second order response. So all the physics of interaction is here in the third order. So what Chi3 entails is weak nonlinear absorption, but it also includes self-focusing effects. And when you focus into material, you also have surface aberrations, which can really distort the beam. So from a Gaussian profile with a minimum spot size and a small depth of focus, lots of unusual propagation effects will take place. And while you're interacting with the material is changing. Once you absorb, it's not the same material, and that provides a feedback back to the beam propagation, which can really distort the dissipation volume. Now that is how light gets in. What happens to the material, of course, happens during and mostly after the laser as the material cools. There's stress, there's compaction, which might give refractive index changes, or rarefaction. There could be bubbles forming. There could be a more gentle forming of chemical bonds, rearrangement that leads to defects, or you could turn on annealing effects. There's also nanogratings forming in the fused silica glasses, which is what we're mostly focusing on. And so the net result is, instead of damage, in here is really the possibility of controlling processes, modifications. And so I like to call this seeking the magic in Chi3. So out of this is a wide range of applications today. Here's sort of a picture show of some of the things we've worked on. Very early in my career, we discovered serendipitously this high repetition rate effect, which turned on thermal heating, which was not supposed to happen. I remember Gerard Moreau saying that this is a non-thermal effect. And so we got a patent on this, and it actually got licensed. It's now, but it took 20 or 30 years to get the technology to catch up with the difficult types of lasers that existed during that beginning time. Now, if you look in here, there's a filament. I'm going to talk a little bit about filaments today and how this actually turned into a commercial product. This heat accumulation effect is what helps us in making low loss waveguides. This is a laser interaction zone down here, and this is the heat accumulation zone. And around here, this is a positive index change. So many groups today are making waveguides, even commercially now is beginning. You can modulate while you're writing. These are grading waveguides, right? Grading. So we're going to talk about that. And this is a woodpile structure. It's actually a cross section of a microfluidic channel, but where we've etched a woodpile, inverted woodpile structure of holes by using chemical etching through laser tracks. And then there's some other interesting physics. I don't have time to talk about this intra-film cleaving, where we can peel layers off by just interference and explosion from nanoplanes. So the end result is there's some remarkable processes. There's much more going on in the field than just what I showed you, but this is from my group's perspective. And I'm going to talk about how we can enhance performance, for example, of fibers, move them from just being a communication highway to actually a processing device. So take some pressure off of, say, the silicon chips or optical instruments and build it all into a more compact fiber, and talk about a spectrometer in a fiber. So let me just start in. So let's begin just with the laser arrangement. There's many types of short pulse lasers, even much shorter than this, but around 220 femtoseconds, you sort of get the price point and power point. We're using a 20-watt system. We have 3 wavelengths with harmonic conversion to 515 second harmonic, and this is where we mostly will be working. So it's a beautiful green light, and basically we focus it into a material. We use X, Y, Z stages or these tuning galvanometric mirrors to get fast scanning. And here's a picture of a couple of members of my group, and there's that visible, beautiful green light, and the laser's this compact box over here. Now, one of the things we'll just start with briefly is work done by PhD student Asen here. And what he mastered for our group was not just focusing the laser, but actually manipulating the laser here with the spatial light modulator. This imposes phase front distortions, which with the lens becomes a Fourier transform. And so it allows 2-dimensional or even 3-dimensional shaping. And we're using this to split the beam to do parallel processing. We can compensate for aberrations. We're making confocal phase fronts to make filaments. So this is really where all the new advantages are coming, to harness laser energy more effectively and to reshape beams to counter what is happening through the optics or in the material, or simply to pattern and get more structure at higher speeds. So, so let's just very quickly take a look at what happens when we focus a laser. So here is focal depth, 44 microns, so near the surface, but almost a half a millimeter deep and almost a millimeter deep. And the surface aberration that I mentioned is an imperfection in Snell's law. And this is close in shallow focusing to what a Gaussian beam looks like. You can see the beam profile, a narrow width and a depth of focus. But as you go deeper, you get the surface aberration. There's the intended paraxial focus, and the beam stretches below. So now when we increase power from low pulse energy to high pulse energy, you get to a threshold of nonlinear absorption. So at low energies, nothing happens. And here is the first beginnings of modification. And these are refractive index changes made with a single pulse. So deep here in the material, we're seeing the effects of surface aberration. But if we go shallow, there's a very tight focus, the intensities are higher, and you see this Kerr effect. The beam is actually focusing, misaligning, focusing higher. And at intermediate depths, you're seeing both a self-focusing and a refocusing effect due to plasma distortions, plus the effect of aberration shift in the beam below the focus. So really the optical, even just getting the light into the material is a game of trying to understand how much energy you can apply and are you going to get the shapes you like. And so you can see where beam shaping is really attractive if you want a flexible processing tool. And you know, we've Asen's published a few papers in this area using the spatial light modulator, imposing phase fronts like this to make filaments. And we're making waveguides. We're doing microchannel etching with controlled shapes. And we're using filaments in a variety of ways that I will just slide into now. So, so in harnessing filaments, I'll just point out very quickly that going back now over 10 years ago, one of my postdocs was very creative with creating filaments, and you could see in forming filaments in glass that you could induce stresses and lead to scribing of glasses. I think I don't have time to talk about some of the studies we did recently, but anyway, filaments turns out to be important commercially today, and these filaments are used as a contactless way, non-contact way of cutting various types of glasses and electronic components today. And the technology ended up being bought out by Coherent, one of the largest laser companies. Today, we're learning how to make filaments in high volumes. You can see these refractive index changes in polymer here, and using spatial light modulators, we form all these modification zones in one pulse, and then we can use spatial scanning techniques to move this around. And by controlling the filament strengths, you can get these kind of colors. This is in a PET type polymer film. So we're hoping we can do 3D printing. Writing the structure inkless below the surface means it will not be damaged by touching or scratching the surfaces. All right, so let's move on to fibers now. And fiber Bragg grating was a discovery by Ken Hill in Ottawa back in the late 80s, and it's now an important commercial device. Very briefly, what you do is you modulate the refractive index along the length at half wavelength spacings. And what this does then is it takes a spectrum of light and it returns a notch, like a notch filter returns a narrow reflected light, or cuts a transmission hole in the transmitted light. So these are used as mirrors and fibers, as filters in telecom systems, or as gauges in all sorts of infrastructure and medical kinds of applications today. So we've played with and tried to perfect writing these in different ways. Here is a filament lined up on Bragg spacings with this cartoon, and it's kind of tricky to build this. Here we're using a glass plate. We're actually using the aberration of the first surface to lengthen the filament, as we showed you. Then we're using refractive index oils to compensate for an aberration here, which would destroy the filament symmetry, and this would stop working. And when you line these all up, you can in fact get these filaments at controlled positions inside the fiber. We have about 1 micron positioning control, and we can get very uniform periods. So there's a top view of the filaments here, and then we can close the spacing up to almost 300 nanometers today. So with that, this is a kind of classic stop band shown here in transmission and reflection, but there's additional coupling here to cladding modes, which can be useful for sensing. And what we did here is, if we can use the filament as a kind of novel antenna shape, we can explore the idea of building an spectrometer. So if you go to a second order Bragg grating, the first order will come out sideways. And we showed that we could tailor the design of the filament to try to make a spectrometer all built into a single fiber. So what comes out is a focus beam of light by the optical design. And if you put a CCD sensor here, you have a spectrometer of whatever light is propagating through the system. So just briefly, here is an 8 wavelength source in our fiber. This is a 4th order back reflection. So here, what you're seeing is a 1st order, 2nd order, and 3rd order light. It's not quite visible here. Now, the cool thing with this device is, because of the filament antenna-like shape, the radiation patterns are confined azimutally to very small angle ranges, only just under 3 degrees. It's quite remarkable, because normally scattering would go into all the angles. So that concentration makes this much brighter. Here we show a chirping, which is basically focusing. So this is a lensless spectrometer. So all the green or red or blue then get focused at a designed distance. And with that, we can narrow the line widths to the sources. And let's just show the final result. So there's a cartoon of the device here. This is a recent publication on the device. And here we're measuring with different sources, line widths, and we're getting about 0.3 nanometer resolution from a device that's about 1 millimeter in length. So it's really quite, I think, an interesting way of making compact optical devices. Now, just very briefly, we can ask another question. What if we scale up the energy? And so the physics of the laser interaction also supports the idea of explosions. They're called micro explosions, but here, this is a filament explosion. And what happens is if you set this up, focus it right, is you can not just change the refractive index change, but you can create a kind of violent explosion, but it's all in submicron scale laterally, and you end up with these holes. And so this actually works. What this allows us to do, these are just simulations of the optical field in the core, and you can get really strong stop band effects that really was not available in the fiber until this time. And so with very strong stop bands, you can make even shorter devices and play with, in this case, fiber Bragg gratings, but just high index contrast. So these are some simulations, say with a pi defect, you can get these notches in the stop bands. And these are different refractive indexes of the holes filled with liquids. So this all really works. You can see strong Bragg shifts. And so here's just a picture show verifying that these holes are forming. So we make our nano hole capillary fiber Bragg grating. This is second order with 1 micron spacing in this case. And we're piercing the core and the cladding, so liquid should come in. If we cleave and polish this at an angle, here's the fiber under an SEM. And as you tune in closer and closer, you see that array of holes, and you infer that they're 200 nanometers in size. So we have characterized these fibers with the holes during writing. You can see the Bragg grating appearing here with increasing number of filaments. So it's real classical fiber Bragg grating. This is a video. Should be a video. How do I? Or is it the next one? Oh, maybe it's going here. I think it's because I'm in the, maybe because my laser pointer is on. Oh, I don't have control with my mouse. Sorry. Here we go. Turn off my laser pointer. There it comes. It's funny. Okay. So what you're seeing here is a fiber drawing by capillarity liquids into fill the hole. So the contrast goes down. So you could actually erase the gratings with index matching oils. And so they indeed do fill very well. And I think you can see my pointer. Let me know if you can't see my pointer. I'll just use the arrow here. So, you know, we can fill these with liquids. We can see the stop bands shift according to lower high index. And so we have shown refractive index sensing is possible here. There's the wavelength shifts according to the air or other materials that have been drawn into the fiber. And you can also, with weak acid, tune the holes, and these are stop band shifts with time as hole diameters increase up to 700 nanometers. So we've really characterized this, and we have a paper in review at Nature Communications on this topic. Here's a paper also just almost ready to appear now in Advanced Optical Materials. We've put liquid crystals into this, and the nano capillaries align them so we can do now polarization control, and we're trying to make it active here in the fibers. So there's a lot of ways of improving the optical fiber, not just as a conduit of information, but also to add features. And just in general, we've done a lot of earlier work on building optical waveguides around the fiber. Here's some, just as an example, here's waveguides we've written into a blank fiber connected, fused to an SMF, a single mode fiber. We built Bragg gratings. And so this is a sensor that measures temperature, and the 3 gratings also measure strain. So you can actually calculate the positioning of the fiber and the temperature. And so this is a simulation measuring temperature locally, and also recalculating the position. And these are actual measurements of a fiber undergoing heating and bending strains. And these are the shifts of the 3 Bragg resonances, which are used to calculate this position, reconstruct the position and temperature. So we actually had tested this this is a pig under x-rays, and we were trying to help guide with the fiber, working with Victor Yang at Ryerson University, a way to help improve the steerability of catheters. All right, so so the lab and the fiber is the idea that we can build photonics, and we can build MEMS or mechanical devices by etching, doing additive or subtractive processing around the fiber. And this is a PhD work of Mo Hak here, who's now at North and Waterloo. And these are just some pictures of the kinds of devices. So to facilitate the fiber and make it a smarter device. So the last part of my talk then is to focus closer to our theme today on Moore's Law. And so while we're not working directly with silicon, we have actually worked with Huawei on some of the packaging challenges. And so what we have today is our information highways based on optical fiber, and our electronics world is rooted strongly in silicon now for multiple decades. And we're not so sure where that's going to go. We have some other speakers who are going to address that. But then we have the interface, and what has happened is silicon photonics is now really well developed. And this is a view from IZM, a Fraunhofer Institute in Germany, of some of the directions that we might need to move in to sort of facilitate the overall system. So we have data coming in light pulses, we have processing electronically, we have silicon chips, and the packaging of all this is really, I think, the biggest challenge today, where the fiber might go to the silicon photonic chip, but the silicon photonic chip is disconnected from the host chip, or it's not intimately coupled to that. And so these are all separate modules. And this is a kind of picture of trying to bring the optics close to the electronic chip to have them better integrated. And ultimately, you end up realizing that you need to build optical circuits with electronic vias. And what that platform will look like is of much discussion today. So bringing the fiber to a board and then distributing the light from device to device is really the challenge going forward. So there's several groups that have been proposing ideas for this. So at the beginning level today, we have edge coupling to silicon fibers. But if you look at the size of the waveguides in silicon and compare it with the fiber, an optical fiber is just a little smaller than this with a single channel. And so there's a routing problem with bulk fiber being too big to match up and have high density here. Another way to sort of improve density is to use gratings on silicon chips and bring fibers vertically. But this kind of vertical coupling, again, is oversized. And so there's lots of ideas being explored on how to bring this down. So I have a couple things to talk about here. I think I'll just, well, what we're going to do is use laser writing, for example, as pointed out here, but we have a different approach than shown here. But the idea is to build optical circuits ultimately that connect with fibers, but also connect with silicon chips and facilitates packaging. So we'll walk you through some of work we did. So this is work that was initially sponsored by Huawei. This is a paper we had published recently. The idea here is we're taking multi-core fibers. So there's 7 waveguides in a fiber. That improves the density already of the routing systems. But the question is, how do you take waveguides that are no longer planar in alignment and route them? And so there's this work by Thompson where laser form waveguides are made in 3D, facilitating these fan outs. And with the fan outs, you can reconfigure the waveguides from the multi-core fiber into linear arrays to do edge coupling. So just briefly, we built an interposer and introduced these multi-core fiber sockets to improve the alignment geometry. This is a traditional silicon photonic chip with a linear array of 84 channels. Here we have 12 waveguides of 7 cores each, so 84 waveguide channels. And then we rearrange this and scan the laser. Firstly, what we do is we scan the laser and chemically etch these sockets. And what this does is the fiber can just plug in and just rotate to the best alignment. This saves a lot of, from 6 dimensions of alignment, it just becomes 1 dimension of final rotation to lock in and light up the circuits. And these are some of the images as laser formed. There's your waveguides, 7 of them here. And we can have chemical etching opening the channel here, and the fiber can then press against this. And there's an end view looking into the socket, and those white zones are the waveguides. And here is how the packaging looks once we're plugged in and epoxied. These are fairly robust, and we now can light up our interposer. And then we are testing the interposer losses. So with this alignment, we can comfortably set under 2 dB, well, except for this one, but we have bend losses, propagation losses with the laser form waveguides. Most of these losses is due to misalignment of the actual fiber. It's not perfectly arranged waveguides. That's a commercial fiber. So in the end, we could attribute, find additional losses due to the silicon chip, the mode mismatch, et cetera. And over 84 channels, we have losses around 7 or 8 dB. We basically are new to this packaging game, and we lost about 3 dB due to packaging losses. This is the creep of the epoxy as we're aligning, but that of course can improve. And so I think this is really a sound technology for edge coupling, and there is a picture of the device. Okay, now just to finish off then, we're also currently working on vertical coupling. So this is going to allow even higher density, but the problem with vertical coupling is we don't want fibers coming straight down. We want a planar optical circuit. And so what we have done is we've taken some ideas that other groups have used on total internal reflection, but we're using laser scanning to build an internal total internal reflection mirror. So by chemically etching out a channel, we can make a reflector. So here's a cartoon showing a design of horizontal waveguides. So this, in fact, is a glass panel, which could be thin. We can mount fibers horizontally onto the edges using the ideas as you see down here. And then we build with lasers, we build waveguides horizontally and vertically so we can access the grating coupler in the silicon photonic chip. And we chemically etch out these mirrors. And here's some of the pictures of the device. So here we're scanning the structures. We have to make access ports for the acids. Because of chemical etching times, we have to add lengths if we make shallow mirrors so that all the mirrors etch to the same zone. These mirrors are working because light coming backwards to this mirror is reflected. It hits this mirror and is shown to us. So this would be dark except for the light coming from here. So we know we have total internal reflection. We're actually getting losses less than a dB per mirror in the telecom bands. So this actually works. And here are some pictures of actual devices here. These are the waveguides. These are the etched mirrors. And so we've just tested this, and this is a first result. So we have about a 5 dB insertion loss on one of our loops here, and we're just trying to build up the circuits, the number of devices, and put a paper out on this work. So the basic idea is that in the future, lasers have this magic Chi3. We can do additive and subtractive processing here. We can build a thin optical platform that can connect with different types of fibers. You can bring light in horizontally. This is showing access from the top. These are the mirrors. And with the thin glass plane, you can etch out holes. You could have electronic components as well as the silicon photonic components in this future direction of an optical backplane. So I'm out of time. I want to thank you. I hope you found this interesting, and I'll stick around for questions. Here's just a summary slide of the magic of Chi3 showing different project areas in our group at this time. So I'll thank my sponsors, and I'll come back to that slide. So I want to thank support from NSERC, and we've had various companies support us over the years. Thank Ontario Innovation, CFI, and MyTex for supporting the research. And I'll finish here. Thanks so much.
Thank you, Professor Herman. That's a beautiful, beautiful talk, and it's very exciting to see what you can do in optical fiber. I invite the participants to write questions and answers either using a Q&A button. If that doesn't work, you can use the chat. But and also ask our speakers to check the Q&A and chat in case there are questions that you can address online. I'm just wondering about scaling. So you can do all these beautiful things in an optical fiber. Are these processes that you can scale up? Let's say that could be taken up in industry to make many chips, or many devices.
That's a very good question, and we've it's been fascinating to watch. In my career, I remember in the 90s, leaders, senior leaders saying you'll never see femtosecond lasers in a production lab, and well, it happened. It's been growing very strongly over the last 5 years. So this is a strong commercial area of broader applications, particularly in electronics, but eye surgery, et cetera. So, so the laser is robust. The power levels are going over kilowatts now. And the question is, how do you harness the energy? And so that's way more power than I could use. That frightens me, that level of power. But there's ways of breaking the beam up. Here in the bottom right, there's something like 90 beams. We can break our low power laser into multiple beams, and using the spatial light modulator, we could do parallel processing to speed things up. I think it really comes down to how much power you want to use, how you can distribute it to many stations. And if the value is there, we've written waveguides in some glass materials like at centimeters per second. So if you're working in 3D volume, that kind of writing approach is attractive, I think. You can't really use lithography and project something into 3D. That's kind of impossible, I think. But I think where you are trying to connect, highly dense photonic chips with a mess of fibers, this can help you arrange things into smaller, compact ways that are going to be commercially viable. So the scaling up is possible. I think the tools are there, and there's been a lot of advances, particularly from some of the Fraunhofer institutes in Germany on exactly learning how to harvest a kilowatt of femtosecond power using various scanners for 2D and 3D processing.
Okay, I don't see any other questions, so I have a second one.
Sure.
I remember that very early on, when in laser writing and so on, there was a lot of material being projected, of course, as you anneal the material. Is that a problem nowadays, or it isn't? I mean, you don't have any.
Yeah, if you're machining a surface, then that material is ejected. And so For sure, it can be a problem. If you're writing waveguides, there's no material ejection. Everything's confined. We use a weak hydrofluoric acid, so that's done in a fume hood, and that's how we remove material. So these are, that kind of process can be done in batch. So you can laser scan serially a bunch of devices and then drop hundreds in at one time in a production kind of facility. If you're just working at the surface of ablation, there's ways to mitigate the debris that might settle. You can work in vacuum, which is cumbersome. You can have gas flow and nozzles. So these are done in cutting kind of applications to reduce debris. So a lot of like automotive applications or where you're welding and cutting have jets of gases that help assist those kinds of processes. So there's imperfections, but even in Moore's law, our transistors have huge imperfections that are compensated in various manufacturing ways. All right.
Great.
Good question.
Good. Well, thank you very much. And thank you for launching our webinar today with this really fascinating talk.
Right. All right. My pleasure. I'm looking forward to hearing other people's ideas for Moore's law. Thank you.
Okay. So our second presentation today is by Professor Adinal Richtenmeyer. And Adina is an assistant professor in the physics department at the University of Ottawa since January 2016. She received her undergraduate degree from Jacobs University Bremen in Germany in 2006, and her PhD in physics from Rutgers University in 2012 in the US. And prior to joining University of Ottawa, she was the Alexei Abrikosov postdoctoral fellow at the Center for Nanoscale Materials at the Argonne National Laboratory. Her research group focuses on uncovering the novel electronic properties of low-dimensional quantum systems using scanning probe microscopy and spectroscopic techniques. So it's my pleasure to invite Professor Richtenmeyer to share with us her talk, Quantum Materials at the Atomic Scale.
Hi, good morning, Marie. Good morning, everyone. Thank you very much for having me in this webinar. And I will try and quickly share my screen. I'll try to get it all in the right presentation mode. Okay, I believe it should be all good now. So I will just assume you see the right screen and the work that we do. So thank you for inviting me to tell you about the work that we do in my lab. In our work, we actually focus on a new class of materials. And these are atomically thin materials. So I put this picture here. In the last 15 years or so, there's a lot of excitement around the possibility of creating materials that are at the ultimate thickness. And with that, both the opportunities for making things smaller, but also the new properties that come about when you try and confine electrons in planar structures, in atomically thin planar structures. And that's a representation of this idea of taking atomically thin layers from materials that are weakly bonded, van der Waals bonded, and creating new structures. And to give you a sense of the breadth of possibilities in terms of electronic and optical properties that these material platform comes with, we have a table here where it's indicated that graphene, for example, the one that's the oldest of this family, it's a semi-metal. But then we also have at our disposals hexagonal structures such as boron nitride, which, because of the different nature of boron and nitrogen, is an electric insulator. And then more complex structures, we call them transition metal dichalcogenides broadly. This family of materials that lots of members of this family are semiconducting with a wide range of gaps. And in addition to the semiconducting, insulating, and semi-metal monolayer materials, we also have a number of materials that, upon cooling down, they have many body states, such as superconductivity or charge density wave, and they constantly in this field challenge our understanding of these strongly correlated physics. As they show all these phenomena at the atomic scale. So as you can see, there's a very wide range of electronic properties that we can play with. And one last thing I want to mention is an important nuance in this field of 2D materials, which is that although oftentimes they're talked about as if you have Legos and you stack Legos, it's quite important to notice that the interlayer coupling, the van der Waals weak coupling between them allows a wider parameter range that you would think with Legos, because it also allows you to rotate them with respect to each other, and it allows you to also change the interlayer coupling between the layers and create these proximity effects between states of different types. And so it's quite a wide range of tunability that you can have in devices and structures made out of these 2D materials, where interlayer coupling, twist, strain, and the electric and magnetic field can really tune their properties. And so in terms of how they can be used for electronic applications, both computing platforms and non-computing platforms, there's a table here giving us some kind of an idea. The authors try to summarize. So for example, in terms of logic devices, the various 2D material structures could be used for transistors, for memory, or for interconnects. And in terms of functional devices, all the way from sensors, which are closer to probably reality, to more advanced and complex ideas around neuromorphic computing. And also, there's an entire wealth of research that is done for sort of non-computing devices, these optoelectronic devices that they're also enabled by 2D materials in their heterostructures. So to give you a more visual sense of what devices that are made of 2D materials look like, for example, in terms of logic and memory, so transistors out of 2D materials can have very different architectures. The classical one would be a source and a drain with a carrier concentration and carrier type being modulated by a gate. And so in this case, you see that just by the nature of the 2D materials, these are planar structures. And it's just interesting, depending on the 2D material that we have in between the source and the drain, you can have N-type, P-type, or you can have ambipolar transcurrent between the source and the drain. And so because of their atomically thin nature, you can also play games where you have tunnel field effect transistors, where you make atomically sharp interfaces between 2D materials, and then you can take advantage of the vertical direction. You can have barristors, right, a barrier in the transistor, where you take advantage of controlling the Schottky barrier, for example, between a semi-metal and the transition metal dichalcogenides, a semiconducting one. This could be vertical, or it could be a lateral dimension. And moreover, you can, in fact, the gate dielectric, you can replace it with a ferroelectric oxide, and you can have further control of the current through this channel. So really a wide range of opportunities. And with these opportunities, of course, come also challenges. And the challenges that you might already infer by looking at these structures have to do with the contact resistance at the source and the drain in these transistors, have to do with the presence of defects in these channels, and I'll get to this, how we address that in our work, as well as, of course, with the encapsulation of using other 2D materials to encapsulate and improve the performance of the transistors, and so on and so forth. Now, also, memory devices are based on sort of properties that occur at this atomic scale. And I'll just give you an idea of some of them. This is a summary of a number of them, but let's just follow a few ideas. So for example, here we have a polycrystalline 2D materials. And in this case, if we try and look at the current voltage characteristics, various phenomena that occur in the plane will lead to switching. And so, for example, a grain boundary in this 2D material can, for example, be used as a memory memristor, or an atomic connection between two pieces of graphene can be a switch. More interesting are also the ones that have to do with different phases of these two materials. So, for example, the charge density wave phase in 1T tantalum disulfide can go from one to another type, and that comes with a huge change in resistance order of magnitude. And so these appearance of the charge density wave upon application of electric field, for example, or temperature, that can be controlled and can be used as a memristor, as a switch as well. Another examples are intercalating lithium ions in between the layers, or taking advantage of the different coordination between the transition metal and the chalcogen, and having these 1T or 2H phases that we call them, whether we have octagonal or otherwise coordination, and then you can apply an electric field and switch between the two structural phases, creating again a switch-like behavior in your device. So really a wealth of possibilities. And again, to emphasize that to make these into practical and devices, we need to address a lot of material challenges. I'll come back to that a little bit towards the end of my talk. So not only these logic and memory devices are thought as sort of part of the classical von Neumann architecture that we're used to computing, but also they're considered for more down the line application, let's say neuromorphic computing, where some of these transistors and memristors can play the role of synaptic transistors, or can have synaptic plasticity through application of, let's say, electric fields and so on and so forth. And as we're talking about next generation computing architecture, we ought to mention the quantum information science. The 2D materials really having a wealth of quantum phenomena are also quite intriguing for the development of quantum information science, which now it's maturing more and more as a field. Yet 2D materials are at this point largely unexplored for quantum information science. And that's also a part that we do in my lab. And so, for example, there is potential for realizing both gated quantum dot structures in 2D materials that could be in some ways have advantage over the silicon qubits that we're more used to. And also, these artificial atom or quantum dots can be realized as single atomic defects in 2D materials, both of which these avenues are starting to be explored more and more. And then other type of research in this area would be taking advantage again of the ease to create lateral or vertical structures in 2D materials, and imagining a new type of superconducting qubits where the superconductor, the normal and the superconductor regions would be made out of atomically thin 2D materials, or going to the topological qubits where one would try to create structures of 2D materials that would create these states at the edges of various faces of 2D materials. And these states can then be a different type of qubit that would allow fault tolerant architecture of quantum computing. So all of these are sort of visions for using 2D materials in quantum information science. So let me focus now on the work that we do in our group within this broader field. And so one of them is using scanning probe microscopy to explore these atomic defects and to explore the 2D materials at the atomic scale, specifically looking for dopants and quantum defects. Another one of our research area is to build devices out of 2D materials and heterostructures, and specifically to try and create gated quantum dots. And this is done in partnership with the National Research Council. And moreover, we're also trying to make sensors out of 2D material field effect transistor, graphene field effect transistors to be more specific. And we do all of that sort of intertwined with trying to address step by step also materials challenges that are probably some of the most important challenges in developing these 2D materials into devices. So let me talk a little bit about each of these. So we start with the defects and dopants into the material. So for that, so to really go down to the atomic level, you need to have a way to probe matter at the atomic level. And if you're not familiar with it, there is a type of experimental techniques that are called scanning probes, which work pretty much like reading the Braille alphabet, where you raster a probe across the surface and you collect information about your surface down to the atomic scale. So in particular, the one we use in my lab, pictured here, uses a metallic tip that goes across the surface and is the quantum mechanical tunneling between this metallic tip and the surface that allows us to collect information, two types of information, one that has to do with the topography of the surface and one that has to do with what we call the local density of states, or in more simply put, the quantum wave functions of the electrons on the surface. And so to be more technical here, if you remember your first assignment in quantum mechanics, it was to calculate the states of a particle in a box. And you found that these states are actually discrete. They're quantized, and they can be labeled with these numbers and the wave function corresponding. So the wave function that describes these states, you can calculate a probability density by knowing the wave function that tells you how likely is it for the electron to be in a certain position, at a certain position in a certain level. And so, for example, for the first level, it's very likely for it to be in the center. In the second level, it's very likely for it to be in this, where the peak are related. So it just gives you a sense of the distribution of the electronic states and the wave function in real space. And what's really remarkable is that the scanning, tunneling, microscopy, and spectroscopy allows us access to this very detailed information about the spatial distribution of the wave functions in materials, which can teach a lot about the electronic states of these materials. So let me give you an example of how we use that. So here we focused on 2D semiconductors, and we want to understand what is the nature of atomic scale defect in these materials. So for example, we would use scanning tunneling microscopy to scan a large area of, in this case, rhenium disulfide is the semiconductor that we use. And the fact that you see these lines across the surface and we measure the thickness, they're really one atom thick structures. And the fact that they're aligned in these directions also tell us something about the symmetry of this material. In this case, it's an in-plane anisotropic material. And as we zoom into the surface, we are also able to see the individual atoms, as you see in this image here, where we also find that they're organizing these rows of atoms in such an in-plane anisotropic 2D semiconductor. So through spectroscopy, we measure this derivative of the tunneling current with respect to the voltage as we apply a bias between the tip and the sample. And such a measurement gives us a quantity that is proportional to the density of state. So in other words, if you're used to semiconductors, you will find that in such a spectrum that we take on a 2D semiconductor, we find the valence band, the semiconducting gap, and then the conduction band. And so in this case, the gap, the semiconducting gap, was found to be around 1.3 eV. And we find that the Fermi level in this particular semiconductor was very close to the conduction band. And as we saw that, it was then not surprising that as we scan to the surface, we find very often these point-like defects everywhere. And we diligently count their numbers. We find that the most common one in this material is so-called type A. And we try to exploit what is the nature of this defect. And to do so, we paired up with our theory collaborators, both at Ottawa, Professor Harlech's group, but also in Europe with Professor Francois Peters. And then they're able to help us by simulating the local spatial distribution if you, for example, remove a sulfur atom, which you might think is the most common type of defect in these 2D materials. However, removing a sulfur atom does not resemble what we see in experiments. And then the idea is, well, can you have an oxygen that was grabbed by this defect from the atmosphere onto the vacancy? And indeed, that starts to look more like what we see in the experiment. And moreover, it appears that such a defect would also come with, well, if it were just the sulfur vacancy, it would have an electronic state somewhere in the semiconducting gap. If it doesn't, if it has an oxygen passivating that defect, it would not have an electronic state in the gap. And so going by these two pieces of information and comparing them to our experiment, we find that very likely oxygen is responsible for these atomic scale defects. And that is adding up to a wealth of experimental results also coming out from other groups on transition metal dichalcogenide. So why are these atomic scale defects of interest? So for several reasons. They can affect, for example, the excitons in these 2D materials. They can affect catalysis in these 2D materials. But also importantly, they were found to give rise to their single photon emitters. And so although people measure them as single photon emitters on the surface, so far there is very little information as to correlating the precise nature of the defect, their location, and the single photon emitting phenomena. And so there's a lot of interest in trying to have more understanding of the nature of these defects and then controlling their position, perhaps intentionally putting these defects at will and creating, let's say, a device out of it and so on. And so the first step would be, of course, to address the question of what is their nature, which is something that we do using scanning probe microscopy. So moving on to another kind of work that we do, in this case, exploring circuits in 2D materials. In this project, the idea is to look back at the wealth of work that was done in 2 decks, creating quantum dots and trying to make spin qubits in 2-dimensional electron gases. So here we paired up with the experts at the National Research Council, which really over the years, they created single quantum dots, double quantum dots, triple, quadruple, with a lot of control over the states, the spin states of these qubits. And so because 2D materials come with certain special features, such as the spin and the Valley degrees of freedom are interconnected differently than in this case. We have a direct gap in the monolayer limit, which means that in principle, if you want to create some kind of a light matter platform, that could be a very efficient way to do it, as well as there's less possibility for interference with the spin state, so longer coherence times might be expected for 2D materials. And so we sort of embarked in this ambitious project to try and use 2D materials and pattern them with gates and see if we can realize quantum dots in this system. It's a very challenging project from a technical point of view. I'll get to that in a second. And so basically, we try and have some local gates. We then, with different width, we place hexagonal boron nitride as a gate dielectric, 20 nanometers in height, a few microns in width. We place metallic contacts on the gate dielectric. We place a semiconducting atomic thin layer, in this case, tungsten selenide. We aim to create a quantum dot over there in the center. We encapsulate this with hexagonal boron nitride, both for protection, but also as a top gate dielectric to further control the charge carriers. Actually, that turns out to be a useful knob for tuning the contact resistance. So in such devices, I will spare you of the details, which are hopefully coming soon in an upcoming publication. In such a complex device, we were finally able to overcome material issues. And we see the stability diagram, which is an indication that we have created a quantum dot. So in regions that are dark blue, there are regions where there is no current, so there's no electron in our quantum dot. The other regions represent regions where the electrons hop in and out of our quantum dot. So we're able now to really isolate regions in this tungsten selenide. And so we're looking forward to playing further with understanding the exact states of this quantum dot, understanding the length scale, the energy scale, and then taking this further to try and connect also with light. So again, I'll emphasize that the experiments are led by the quantum transport experiments are led by our collaborators at the NRC. All right, so another aspect of our work is to make 2D material devices for sensing. And so in this case, the premise of the device is pretty simple. So we have a graphene field effect transistor with source and the drain are pictured here. The gate is missing in this picture. But the idea is that you can have analytes that are in the atmosphere, and as they interact with the graphene surface, they will change the resistance of the device. So the sensing mechanism is essentially monitoring the changes in resistance as we have these analytes covering the surface. And so this is a picture of such a device that we can create in our lab. And with this type of device in the last 2 years or so, we've been able to understand and do detection of volatile organic compounds such as ethanol. And more recently, we're also interested in simulants of chemical warfare agents. So this work is funded actually by the Department of National Defense. And so to give you a sense of what the science is behind it, if you measure the resistance of a graphene field effect transistor as a function of backgate voltage, you'll find essentially this low and then high and then low again. It's an ambipolar field effect where the highest resistance represents the Dirac point in graphene, or the neutrality point. So that's where graphene is least, it gets more metallic away from that Dirac point. It's most resistive close to that Dirac point. And the very simple field effect can be applied, the very simple way to tune this Fermi level through the Dirac point and make graphene p-doped or n-doped is really to apply backgate voltage. So in this case, for example, our devices, our graphene field effect transistors start off by being p-doped. And that has to do with the type of residues and nanofabrication that we do on the surface. And as they start out being p-doped, if you have a molecule now that will remove further electrons from the graphene surface, you'll essentially become even more p-doped, and so your resistance will go down. So that is one of the possible sensing mechanisms in these type of graphene sensors. And so what we notice here, this is the response of the sensor as a function of time, where the blue colors represent, or the green colors represent times when we introduced ethanol into the chamber of the sensor. And so the resistance goes down as the ethanol removes the electron from the graphene, and it goes more and more sensitive as we introduce more and more ethanol. So this is work we've done to understand the mechanism of sensing and to really understand how to control sensitivity. They're highly sensitive because of this very low density of states around the Dirac point. But of course, sensitivity is not enough to make real sensors. You also need them to be selective. And so towards that goal, this is work that is now published. It's also being written. We've been using functionalization of the surface. So we've been using metal-free thiocyanines and copper thiocyanines. These are prepared in my colleague Benoit Lassard's group. We place them on the graphene surface. And what you see here is atomic force microscopy imaging of copper thiocyanines and metal-free thiocyanines at different coverages. So we have control over how much we cover the graphene area. And what's really neat is that at different coverages, these sensors have different sensitivity towards the analyte they were trying to detect in such a way that you can build a table. And then you can have an array of these sensors. And the response of these sensor array is essentially a fingerprint for every single analyte that you detect. And so we've been playing with this. Again, this is unpublished data. We've been playing with this in such a way that we can detect certain volatile organic compounds by simply looking at the response of these sensors in the array. So that's quite an exciting avenue for exploring sensitivity. All right. So as we're trying to make all these cool devices, we always run into materials challenges. So let me tell you very briefly, what are the materials challenges we ran into and how do we try and solve them? One big material challenge in this field is to have scalable automated transport and layer assembly. Big challenges around proper layer assembly in heterostructures. Others have to do with contact resistance, especially as it relates to semiconductors, controlling the Schottky barriers and so on, as well as doping, understanding the nature and the amount of doping in these materials and the defects. Another big issue as we look forward to using them in application is designing inline metrology tools. as well as, of course, wafer scale growth. So a lot of the things I'm showing you, they are sort of, micron size devices. They're wonderful, but if we want to use them in devices, we want to also have a way to grow them at device scale. So work that we've done in this space, for example, is using a laser light to flatten. So as we transfer, let's say, graphene onto a semiconductor, we try and make these heterostructures, we find these ripples and wrinkles, which are as a result of the van der Waals interaction. Think of it as putting saran wrap on a surface, right? You'll have bubbles trapped in, and so on. But of course, we want to flatten these for devices. And typically heat is, you put them in a furnace, you heat them up to a certain temperature to flatten them. But that may not be desirable in a complex circuit where you have different components that are heat sensitive. And so we came up with this idea where we have laser that comes into a localized area and provides heat to the trapped gas in the bubble. And as a result of this heat, the contents of the bubble may escape through the sides and flatten the surface. And by doing that, not only is this a practical way to flatten the 2D materials, but we also learn, interestingly, a lot of things about the adhesion energy of these devices to their substrate. So that was a neat demonstration. I'm showing you here more clearly. So this was before we did this laser raster flattening, and this is after. As you can see, now we've improved the surface by having all these tiny little bubbles now coalesce into larger bubbles and leaving behind microns of free and good interface between the two materials. Another important development that we've been discovering as it relates to contact resistance specifically is this is a device that I've shown you before in the context of making quantum dots. These are the local gates. There is a 2D material and there's these contacts on top. This is atomic force microscopy image. And we followed this paper that describes how you can use an AFM tip to clean residues off 2D materials. These residues come from the nanofab process. They're typically polymers that you've used for the lithography. And so indeed, we control the parameters of the contact between an AFM tip and the surface to really move, and we call it nano brooming, to move to the side these contaminants, leaving behind a very good surface. And so with that, we were actually able, so it's this technique that allowed us to have good electrical contact between the source and the drain and the 2D material to be able to create quantum dots. And regarding inline metrology and finding ways that can assess the quality of a 2D material film, one thing we have used is in collaboration with my colleague Jean-Michel Menard's group, a terahertz spectroscopy group. We've made these devices where CVD graphene was placed, or graphene grown by chemical vapor deposition was placed on different substrates that are of interest for semiconductor industry. So we've used, as you can see here, silicon oxide, different preparation for silicon oxide, different resistivity for silicon, as well as certain polymers and silicon nitride. And so we've explored using the terahertz spectroscopy signals. We've explored the electronic quality of the films depending on the substrate that they have, and we try and understand the differences between the different substrates. But nevertheless, this entire work demonstrates that terahertz spectroscopy could potentially be a good way to sort of incorporate it into the inline metrology of 2D materials. And lastly, I want to advertise up-and-coming capability at the University of Ottawa, led by my colleague James Gupta, where we have this new system that will be able to, it's being currently installed to be able to create MOCVD large area wafer scales of 2D materials. Specifically, we'll be able to do graphene on sapphire, boron nitride on sapphire, as well as tungsten disulfide on sapphire. And then, of course, we can use transfer techniques to place them on whatever substrate of interest. And so it is a big, big question in the field right now. Can we design methods for wafer scale growth of these 2D materials, and not just of the 2D materials, but also of their heterostructures, lateral or vertical heterostructures. So more of this work, hopefully in the future. So with that, I'll just like to sort of one more time highlight the different type of experiments I've mentioned. So we've been looking at the nature of quantum states, atomic scale defects in 2D semiconductors. We're building more and more on this, making gated quantum dots in 2D semiconductors for spin qubits and sensing. And we're also using the surface of graphene as a very sensitive and more recently selective platform for airborne chemicals. And as we do all of that, we try and also innovate as it's much needed in terms of materials and interfaces for these devices. And with that, I'd like to thank you. This is our lab. We're grateful to be funded by various agencies. So we have access at the University of Ottawa to clean room facilities, to material characterization facilities. And this work is funded by NSERC, DND, and partly collaborating with the National Research Council as well. So I will stop here for now.
Thank you very much, Adina, for a fascinating talk. I don't see any questions in the Q&A or the chat, so if you have any questions, please use those. So I will use my privilege to to ask some questions, Adina. So I was interested by your sensor application and the volatile organic compounds, and I'm wondering what chemicals you are envisaging.
Right. So one of our first targets were volatile organic compounds, so ethanol, methanol, acetone. So these would be so primarily as a proof of concept, but also they are, if you look at papers, they typically detect ammonia or very polar molecules, much less so volatile organic compounds. So there's a need to develop more sensitive sensors for these volatile organic compounds. And so down the line, these could also be used for breath analysis. So that would be a space of application that could be relevant for them. But also, in addition to these volatile organic compounds, we focused more recently through our DND effort on stimulants of chemical warfare agents. So DMMP is a stimulant of sarin. And so, of course, we can't test sarin in the lab. And so you use a stimulant, but then we paired up with the Fury collaborators, and it's really fascinating. They do these molecular dynamic simulations, and they can calculate the charge transfer between sarin or DMMP and graphene, and we can confirm that, at least theoretically, indeed DMMP is a good stimulant of sarin. So there's reason to expect that it would do the same.
So I was told that one of practical applications for detecting volatile organic compounds was in gas stations, because as you fill your car with gas, and maybe that will be something of the past with electric batteries, but there's a lot of course volatile organic compounds that are not good for your health, especially if you breathe that in all day long, especially if you work in the gas station. So there are things like that, and the other, of course, the other site is hospitals, right? And eventually you can detect or biological molecules that would be quite interesting from the perspective of a built environment.
Yeah, I think there is much more work to be done there. A lot of work is focused on, sort of here and there applications, but there's much more work to be done in terms of systematically going through different functionalizations and building these fingerprints for gas sensor arrays. So I think this project is going into that direction of building arrays. So one device at a time.
We have a question. So the question is, what is the wafer size capacity, the maximum size to fabricate 2D materials with the new instrument at U Ottawa?
So I believe it is 4 or 6 inch. But you can always follow up with me by email so I can look into the specifications for this new capability. But it's at that, I think 4 inch is probably a good number.
Is there, so I noticed you mentioned Sapphire Substrates.
Mm-hmm.
Is that because of that you need to have the lattice constants match, or?
So that does have to do with the specific epitaxy for the processes that are developed already. So as this is a completely new platform, there are some initial recipes that were developed, and those are on Sapphire. But in sort of using this instrumentation, some of our plans are to try and grow it on other substrates as well. And that's completely unexplored. You know, the instrumentation allows us to mix the gases and apply the temperature, but yeah, that will be part of the fun using that equipment.
Great. Well, I don't see any other questions, so Adina, thank you so much for a fascinating talk, and we'll go on to the next speaker. Our next speaker is Professor Lee Chen. Lee Chen received his bachelor's degree from Tianjin University in China in 1991 and his master's and PhD from the University of Alberta in Edmonton in 2000 and 2004. And Dr. Chen has been a faculty member with the Department of Electrical and Computer Engineering at the University of Saskatchewan since 2006, where he was endowed with the Barhold Chair, Professor in Information Technology. He was promoted to Associate Professor and then Full Professor in 2016. And his main research interests are radiation effects and fault-tolerant microelectronics. He has more than 100 publications in refereed journals and conference proceedings. So it's my pleasure to introduce Dr. Lee Chen to speak us about the radiation effects in advanced CMOS circuits. Thank you.
Okay. Yeah, thanks, Chairman, for the introduction. Okay, I'm sharing my screen. So you can see it now, right?
Yes.
Okay, yeah. Okay, so today, good morning, everyone, and I give a talk about radiation effects and mitigation techniques in advanced microelectronics. So first, I just give briefly of the outline. So I try to introduce the radiation effect first, and then I describe a few projects that we have done, and also I mentioned a little bit about ongoing projects. Okay, so the first, this slide actually is quite a famous slide in the radiation effects community. So here's Earth, where we are living, and here's the sun. And basically the radiation environment is summarized in this diagram. And we can see that the sun not only brings the photons, basically that's the light, right? Actually, it also brings a whole bunch of other particles with the solar event. Those ones include protons and heavier ions. And those solar particles are the dominant particles in the solar systems. At the same time, actually, we also have some galactic cosmic rays. Actually, those are very high energy, hydrogen and heavier ions. They're from the outer space. And then once those particles approaching the Earth, because fortunately our Earth have a magnetic field, right? And then it formed a shield, basically shielding out most of the particles. And so this is why we can have a peaceful life on Earth, right? And because of the magnetic field, actually some particles are trapped around the Earth, and you can see it here. Depends on different type orbit, and so those could trapped particles could be electrons, protons, and heavy ions. And then on the Earth, actually, we also experience the neutrons. The neutrons are mainly is caused by the very high energy cosmic rays, and when they're approaching the atmosphere, they generate those neutrons, because neutrons does not interact with other particles and then atmosphere, and they can reach the Earth with high energy. And those are one of the major sources at the ground level and atmosphere environment. That's the major radiation source. Okay, and then with this, when we live in this kind of environment, actually the radiation can affect the operation of electronics, right? Actually, there are different type of effects. One actually gradually degradation. Okay, for example, the parameters and leakage and those parameters, and also due to the single event, they can lose the data or even some serious failure. And if we category divide into the different type of effect, normally for CMOS, we have two type of effects. One actually is a total dose effect. And generally speaking is that causes parametric degradation. And then there's other effect with a single event effect. It causes transient effects. And actually the problem generated by the radiation can change actually as device scale. We'll look at that a little bit further. Okay, and so let's first look at the total dose effect. For example, here's the cross-section of NMOS, right? This is the gate, and this is oxide, and this is a channel, right? And then once we apply the radiation, for example, gamma rays of particles, so what happened, they will generate a lot of electron hole pairs in the oxide, okay? And then after a short time, we know that most of the charge electron hole pairs, they recombine, right? But there's still some of them remain. And then the electrons, because they have a much higher mobility in the oxide, right? And so then they will basically escape to the gate. And then only the holes, positive charge left, right? And because if we apply a positive gate, a voltage on the gate, and what happened, then the positive charge gradually move to the bottom of the oxide. And obviously, and then they get trapped at this oxide interface. And we can see that with this positive charge, it will affect the operation of the NMOS transistor. Basically, they're causing leaking. Right? If we build too much charge, and of course this transistor even just simply turn on, and then this transistor is not functioning anymore. So, so basically that's the major effect for the total dose. And I can give you an example. So the effect actually is dominated by the gate oxide. For example, at here we look at the diagram is the oxide, gate oxide thickness, and this is the threshold voltage shift over the dose. We use 1 unit megawatt. Actually, it's larger unit, but we can say that when the gate length is 0.8, this kind of technology actually oxide is 20 nanometers, and then the threshold voltage shift is 1 volt per megawatt. So it's larger voltage shift, right? And then at 0.18 micron, the oxide thickness is 4.3. The threshold shift is actually very small, only 2 millivolt, 1 megawatt. So basically, it indicates that because this technology is scaling, right? And then the deep submicron of this nano CMOS technology is become possible for radiation tolerant applications. This explains why nowadays we can start to use commercial technologies, CMOS technology used for space and many other radiation applications, just because this total dose effect actually get greatly reduced. Of course, the leakage path still exists between and inside the transistor because of the oxide, but relatively is much less significant compared to the older technologies. And in our campus, we do have a cobalt 60 chamber. Actually, for example, we have this low dose rate and high dose rate chamber that can be used for total dose testing, and we have used for many years. And then the next effect is a single event effect. Single event effect actually that generated when the particle upset the state of node, creating an upset event like a flip bit, a logical state change, and a computation change. And then we can group them into many different types. For example, single bit upset is one bit flip. A multiple cell upset is a multiple bit flip in memory flip-flop. And the multiple bit upset actually is a multiple bit in the same word. And actually this is a kind of a more critical because if a multiple bit upset in the same data word and then the error corrected coding may not work properly, right? And so we'll pay more attention to this multiple bit upset. And also we have the same single event functional interrupt and the single event transient. And transient actually is a transient pulse generated in the conventional logic. And those single event we normally call the soft errors because they will not really cause device damage and only it can the data can be recovered. And of course, we also can have some more severe single event, like single event latch up. So basically, it's a latch up, but it is triggered by the ion hit. And also, we can even have a single event burnout. So basically, the device destroyed. This is more related to the power devices. Okay, now I just use this slide to try to describe this single event effect mechanism. So let's look at this diagram. So what happened, this is a pin junction, right? Reversed biased pin junction. And then when a charged particle hit this pin junction, what happened actually is that they'll enlarge this depletion region. And then we call it the funneling. And then along this track, this ion will generate all bunch of charges, basically electron hole pairs. And those charges eventually will be, when the ion penetrates on the path, and they will generate a very short current pulse once the charge is collected by this node. And so this magnitude and the pulse width depend on your circuitry and technology. And however, anyway, if this charge is large enough, absorbed by this node, and it could flip the logical level, right? And it could cause even further problem for the circuitry. So this is the fundamental of the single event transient. Another one I want to mention that used to be we are not really worried about too much about the radiation effects at the ground level. However, nowadays, because this device becomes so small and transistors even get upset with neutrons, and because we know that actually the neutrons they do exist even at the ground level because of the high energy particles from the space. And what happened is that when this neutron hit the silicon device, and what happened is that they will hit the nuclei, and then they generate all the secondary particles. For example, this aluminum plus all those alpha particles. And those particles are charged particles. And those we call the secondary particles. And those secondary particles will then possibly interact with the transistors and generate upset. So this is one of the major problems for the electronics even at ground level. Now let's look at one picture. Basically, it's a trend of the soft error rate with scaling. And we can see that this technology is scaling from 180 nanometer to 7 nanometer. And then here is the y-axis is soft error rate. We can see that actually the soft error rate for a single cell actually is error rate is getting smaller. The reason actually very simple, because the 7 nanometer the cell the size is much smaller than 180, right? And so the single cell rate is getting smaller. Eventually, for this FinFET, you can see that when we use the FinFET technology, and this one becomes smaller because it have a thinner diffusion in the drain and the source layer. However, the problem actually is that with the 2-bit and multi-bit offset rate is increased. The reason is also very simple, because the cell size is getting smaller, right? And then when we put the SRAM cell together, and then easily one ion hit can generate a multi-bit offset, right? And so that's why we call the 2-bit multi-set probability actually increase. And then if we look at the chip level, soft-error rate is also increasing because of this multi-bit offset. And if you look at the chip level, multi-bit rate is also increasing. So it means that actually, even if the device is getting smaller and the single bit cross-section smaller, but overall at the chip level, the soft-error rate is still increasing. So it means that we have to still have to figure out a way to deal with them. Okay, now let's just look at a simple example for the soft-error impact. Okay, for example, if a cell phone with 4 megabyte low power memory with a soft-error rate of 100 feet per megabit, and if in this situation, what happened actually is that generally speaking, is that every 28 years, we have one soft error. It looks like it's not a very big problem, right? But however, if you look at a high-end router with 10 gigabit of SRAM and soft error rate of 600 feet per megabyte, and then it will one error every 170 hours. And if you have a router farm that uses 100 gigabits of memory and one potential network error every 17 hours, okay? So basically means that then if for those servers and large systems, if without proper protection, actually those soft error rate could be very large. And also if a person on an airplane over the Atlantic at 35,000 feet with a laptop with 256 megabit of memory, and then one potential error every 5 hours. So that explains that actually if you're working on with your laptop on a flight, if you're on satellite, or even worse, right? And so every 5 hours, so that could be a big problem. Okay, so then in terms of in this field, actually, because once we have some electronics and for space or even for ground level, and we always need to figure out how to test them, right? And the standard way actually is that we use ions to do the testing. And then when we use ion, then we have one way to measure the energy deposit into the device. We use a linear energy transfer. So basically is that we divide the particle energy loss per unit length by the density of the material. So then that's a way that we measure that how much energy we deposit into material. And then once we have that one, we have the SE cross-section. Basically, we define as a number of events divided by fluence of the particles. And we use this one to measure the sensitivity area of the device. And then, however, with the ion testing problem actually is that, for example, in Canada, we only have a TRAMF that have the accelerated proton. And we don't have a high ion facility. So basically means that this accelerated particles facility is not easy to access and quite expensive. So then in this field, we come up with this another approach. We use laser. And basically mechanisms actually is that the laser light can interact with silicon to generate electron hole pairs, right? And they can generate the SET pulses similar to those one by ions. And so then we can use this pulsed laser to mimic this ion hit, and then we study the single event. So the advantage actually we can provide precise spatial and temporal information, right? Because we can control the location and timing. And it's very good debugging tools. But of course, there's one of the disadvantage actually is that it's very difficult to directly correlate with the ion cross-section with the laser cross-section. So that's the community is still working on that. And in our campus, we build a custom designed laser facility just for this single event study. So here we have the laser source, and actually this is a femtosecond laser, and so we use 2 photon effect to generate the pulse, and then we observe the effect. So actually, right now we try to build this laser facility as the open lab, and so then the other users can use this facility. Here's a sample stage. You can see that the lasers go through this objective, and then the chips on here, we need to decap the chip, and then the laser can go through the chip to generate the offset. I just give one example of this study we used. So for example, this is a CMOS phase lock loop chip, and here we have a bunch of different type of circuitry. For example, this is a inductor, I guess, and here's some other type circuitry in the PLL, and we divided those this array into the different zone, and then we scan these ones with the laser, and then we can find out which one is more sensitive. And then we can look back into the design and figure out why they're sensitive. And so this is just one example. Okay, in the next slides, where I will just introduce a few projects. The first one actually is that is we worked with MDA, and this is supported by CSA and NSERC and the CMC. So the purpose actually is that we have worked with MDA for quite a few projects. For example, we studied this voltage regulators and references, so to see that which one are qualified for space applications. I just want to show you one example. For example, here we irradiated this voltage references RSL 21070, and actually it's floating gate with high precision, low noise voltage reference. And during the irradiation, we found out actually the output of this reference dropped very linearly with this total dose. And sounds like actually it's a very interesting, like a dose meter. And so then we later on we rated even with protons, and we also found it's very linear with this total dose in the output voltage versus total dose. And it's kind of byproduct, and then it be used for the one of the payload of the USASC satellite CubeSat project. And we also, when we work with MDA, and we use proton testing on different type of GPU processors. For example, the one is from TI, two from NVIDIA. And we evaluated their performance with a proton, and we found out actually those ones are suitable for near-Earth orbit applications. So the reason to study those projects, because in the future, right, onboard processing, for example, at the spacecraft and the space stations, onboard processing become more and more important. So we want to evaluate those ones potentially for space applications. And we also studied the FPGA and those other sensors. For example, actually this one is used for Mars, and we use laser to evaluate the sensitive areas of this Hall effect sensor. Okay, and besides we studied the radiation effects, we also developed some radiation tolerant flip-flops and SRAM and CPUs with this 28 bulk and FDSOI. And we worked quite a few universities together, and the project is supported by Cisco, NSERC, ESA, and the CMC. The reason for why we want to study the flip-flop actually is that the flip-flop, beside the SRAM, the flip-flop is the major source, because they are very sensitive to the radiation single event. So this is why we want to develop this radiation tolerant flip-flops. And for SRAM, because we can use the ECC relatively, it's more straightforward. And here, we developed quite a few test strips with bulk and FDSY 2865, and so I can use this one to show the result. Here you can see that actually this is the cross section we measured from 28 bulk technology. And here is basically the LET, so it shows that how severe the radiation of the particle. And this y-axis shows that the cross-section, or you can just think about soft-error rate, okay? And if you look at here, this is the bulk 28, and this is the bulk 20. And this purple one actually is a 16 nanometer FinFET, and this is orange one actually is 28 FDSY. So compared to the 28 bulk and this 28 FDSY, the soft error rate is about 2 order difference smaller. So that one actually is a very, the result is very interesting. It shows that actually FDSY technology is very attractive for this application where low soft error rate is required. For example, like autonomous cars, right? The automobile industry and even for space applications. And as far as I know, so far actually NASA and ESA, they are building 2 large projects based on the FDSY technologies, just because they have a very low soft error rate. And then we also studied some other features in this technology. For example, we try to measure the single event transient pulse width. The reason to measure the single event transient pulse width because once we know the pulse width generated by the particle, then we are much easier to figure out the mitigation techniques. But however, the transient pulse width is less than about from 10 picosecond to 1 nanosecond. So the pulse width is very short. So how to measure those pulse width on the chip actually is very challenging. We come up with a different type of detecting circuitry. For example, the classic detector and veneer detector and pulse filter detector. And then the result shows that actually the cross section from the logical gate still basically we can see the cross section is the soft error rate. Okay, from the logical gate is still. This is the cross-section rate, and then this is from the flip-flops. We can see that from the logical cross-section still much smaller than the flip-flops. So it basically means that in the digital system, the storage cells still dominate the soft error rate. So we quantitatively have some measurement for this technology and we also measured the pulse width of this technology. So that's quite useful for this community. And the last one I want to mention that we have done actually is that we designed quite a few ARM M0 core. We put them on a single chip. For example, this is a reference core, this is hardened core, this is another hardened core. And so we have those hardened cores, and then we compare the performance with this reference core. And we hardened the SRAM. We use the TMR module to protect SRAM, because if we don't protect SRAM, then SRAM will be dominant source, and then we cannot really compare the contribution from the cores. So this research is very interesting, is that because we put all the cores on the same die, and then we can easily compare their performance. And the result shows that actually for the reference core, on hardened core, the dominant error is from flip-flops, and then for the hardened core, the dominant error actually is from the combination logic, and then also from other clock tree and reset tree. We also noticed that actually if we only protect the flip-flop, actually the result is not that significant. So basically that means for complicated digital systems, more protection are needed. For complex system. Okay, basically probably this is the last slide. So beside those projects, currently we're also evaluating the soft error rate of convolutional neural networks implementation on the FPGAs. So we study different acceleration platforms and see that their impact to this software rate. And right now we also study this 12 nanometer, 22 nanometer radiation tolerant flip-flop and memories. And we already have this 22 nanometer test chip ready, and we're going to do some testing. The last one that actually I want to mention is that we're developing this radiation tolerant RISC-V SoC with 65 nanometer and 22 nanometer technology node. Why we are interested in RISC-V core? Because the RISC-V is open source core, and so actually that's very attractive for space and for some of these commercial applications. And our target tape out will be this year, and we should be able to get some result at the next year. Okay, so basically that's conclude my talk. Thank you.
Thank you very much, Dr. Chen. I guess this problem has existed for a long time, and I wonder whether you can comment on other semiconductors, like the wide bandgap semiconductors that seem to be more radiation tolerant. Is there, for long-term space travel and so on, is there a move to change to wide bandgap semiconductor electronics, or not?
Yeah, actually, that's a very good question. Those wideband, and yeah, they're more radiation tolerant, and actually the radiation effect community are very interested in those devices. And for example, actually there are many studies on that. But for the applications, however, those ones still have some integration problem, right? Eventually for digital circuitry, and then for example, the SpaceX, those low cost like Starlinks, right? Those are low cost applications, and so far they are more rely on those commercial CMOS. So that's still the current situation, but I do hope that in the future we have the other materials, and they have with more development, and eventually they can replace this one, and that could be very interesting.
So I wonder whether you can say a little bit about, so what are the mitigation techniques right now? Is it, suppose you're on the space station, is it more shielding? Or backup systems? How do we currently mitigate for those problems?
Yeah, actually, there's also very interesting. So for space, it's really true. Actually, I didn't mention this shielding. Actually, shielding is a very common technique. Actually, for example, for the space station, most of the electronics we always have a 0.1, 0.2 milli aluminum shielding. So basically, that's almost like a common practice. And however, there's a different type of radiation effects, right? For the shielding is more effective for this total dose. Basically, for example, those gamma rays, X-rays, right? And so photons, they can relatively easy to shielding with these metal layers, thin metal layers. But so that's very effective for the space stations. Yeah, that's more for that protection. But for the single event effect, that's not very effective. The reason is that because particle is very high energy, right? And then if you want to really shield them, you need quite 3 or 5 meter of concrete. Obviously, that's not very effective. So for the space applications, most of the shielding is for the total dose. So this is why nowadays the research more move to the single event effects, because single event effect is not very easy to mitigate by shielding.
Okay.
Yeah.
Very interesting. I don't see any other questions, so I want to thank you very much for the insights that you provided today on, a problem that comes hand in hand with our using electronics. And so next time we're in a plane and we crash, our computers crash, we'll know why.
Yeah, thank
So
you.
thank you so much.
Yeah.
So finally our next and last speaker is Professor Maggie Schaaf from University of British Columbia. And Professor Schaaf was born in Handan in China. She's currently an associate professor with the UBC Materials Engineering Department. And she received her bachelor's in material science and engineering from Tsinghua University and her master's and PhD degree from the Massachusetts Institute of Technology. And before joining UBC, she worked at IBM Semiconductor Research and Development Center. And there she led the research and process modeling and simulations for 32 nanometer node CMOS technologies. Professor Schaaf is an expert in silicon germanium materials and devices, and her group has a strong presence in the area of silicon germanium and silicon germanium carbon processing and modeling. And process models from her work have been widely used in practice and implemented in the state-of-the-art semiconductor process simulation tools. In recent years, her research interests have expanded to germanium lasers and monolithic 3.5 laser integration on silicon and germanium and gallium nitride transistors. So it's my pleasure to invite Dr. Schaaf to share with us her talk, Silicon Germanium C, and Germanium for next generation of microelectronics and photonics.
Okay, Chair, thanks for the introduction. Can you guys hear me all right?
Yes.
Okay, great. So let me share my, my talk slides. Yeah, can you see the slide in one screen, not two separate screens?
One screen.
Yeah, okay, wonderful. Yeah. So yes, hi. My name is Guangrui Xia. Actually, in this field, I go by Maggie. Actually, it's my informal English name, because really my Chinese name, for a lot of Chinese even, it sounds very like a boy name. Anyway, so I got my informal name as Maggie. So I have been working on silicon germanium since my graduate school, and when I worked at IBM, I worked on 32 nanometer node. You can see that it has been a long time. So after that, I joined UBC, and I started working more on silicon germanium carbon. And really, that is because we have a long time sponsor, Texas Instruments, and they have been the largest player in the BiCMOS market, in the analog IC market. So we have been working with them for about 10 years on silicon germanium carbon. So today I'm going to cover some of the silicon germanium carbon business, heterojunction bipolar transistors, HBTs. For CMOS, since really in Canada, there's a very little industry that are still working on CMOS fabrications. So basically, I don't know any real hardware fabrication companies in Canada for the time I've been here. So there are a few simulation tool software companies that are pretty advanced. So for example, we have a Crosslight, they are still working on CMOS modeling. They are in BC. So then, as I said, I worked a lot on HBTs. Then another interest of mine is on germanium lasers, which I will actually discuss today. Since I also work on gallium nitride, but since today is more on beyond more, I will not talk about that. So basically, since my talk is going to be on material innovations involving germanium, the first question I actually want to address is why germanium? And I'm sure that it's to many, it's obvious, but germanium has a lot more than just being a column 4 elementary semiconductor. So basically, germanium is the most silicon-friendly semiconductor, so that is obvious, and it's fully compatible with silicon fabrication. So this is a big deal. because a lot of 3-5 compound semiconductor, they have perfect performance as lasers, for example. But because they are not compatible with silicon fabrication, for example, they become dopants for silicon. So it's hard to introduce a 3-5 compound semiconductors in silicon fab. So that's a big problem. Whereas germanium has been fully compatible with germanium, has been routinely processed with silicon. So that is not a problem. And also one thing I want to talk about is the band gap. So here we actually see the direct band gap and indirect band gap. So there is a direct band gap. So although it's not the smallest band gap, it's very close to the indirect band gap. You later see that we can do band gap engineering to actually make the direct band gap to be much closer and sometimes even smaller than the indirect band gap. So band engineering can be done, band gap engineering can be done to shrink the gap. Also, we see a larger lattice constant, about 4.2%. This is tremendously useful and has been widely applied as a stressor. So silicon germanium are commonly used stressors in CMOS. So since the early 2000s, commercialized and still being used in FinFETs. Higher hole mobility, so good PMOS material. And another thing that is not discussed a lot is on this material being lattice matched with gallium arsenide. So the lattice mismatch is really tiny. It's about 0.07%. So basically germanium as a material it has all these good properties. So therefore, in microelectronics applications, they are used in transistors, are used in strain and band gap engineering. For photonics, germanium is also widely used. So they're used as IR, photodetectors, modulators. And today I'm going to talk about germanium laser. It's not often discussed. And also another point that I'm going to talk about is how we use germanium as a platform material or transition material between gallium arsenide and silicon. Or we can just use germanium as a platform material or substrate material to have 3-5 devices on germanium. So that's kind of the scorecard for germanium. And as I mentioned, not only in germanium, we have all these alloys, right? With the silicon germanium alloy, the X or Y can go from 0 to 1, and they can form heterostructure. For this heterostructure, we can have different devices. If we take germanium Y, Y is 100%, then we have germanium photodiodes, modulators, lasers. And if we take germanium to be below 30%, which is normally the case for heterojunction bipolar transistors, then we have silicon germanium HBTs. And they're also used in quantum wells, nanoclusters, and in MOSFETs, as I said, silicon germanium are used as stressors, and silicon germanium also used as channel materials and also in tunneling FETs, etc. So wide range of applications. So this one is a, you can hardly tell that this one is a state-of-art MOSFET. So today we're talking about the nano sheets. Remember in the FinFET area, which was like maybe still in mainstream production, but this one is a research paper. And instead of having fins, here we have a stack of 1, 2, 3, 3 nano sheets. And the 3 nano sheets are actually made of silicon and germanium. You'll see how this one is an element, EDX, element map. So this is the first one, the gray color is just a regular STEM image, and all other colorful ones are the element map. Okay, titanium is the gate material, hafni dioxide, here we actually see hafni, so that's the gate dielectrics. And really you'll see this nano sheets has silicon germanium in it because they are better for hole mobility. So that's in 2 to 3 nanometer node technology. So that's in research. And also germanium MOSFETs has been mature in research, but it's just waiting. I think it's waiting for the right timing to be implemented to in commercial products as a germanium MOSFETs. So this one is a 7 nanometer node, silicon germanium entitled FinFETs. And now, so I'm going to talk another very important transistor. It's called heterojunction transistors. So here we're seeing the cross-sectional image, and it's well colored and good presentation. It's a classic picture of HBT. So basically, really here we are looking at the NPN bipolar transistor. And of course, the other are just all this copper contacts and emitter base collector. And this is silicon germanium is this orange piece of material that is shown here. So basically, it's HBTs are really in the heart of analog ICs. They are widely used in wireless communications and optical communications. And one thing that we have been working with Texas Instruments is on the vertical doping profiles, so NPN and also PNP. So the scaling of HBTs is to make this base narrower and narrower, and higher and higher germanium and carbon we need to engineer to the best value to actually to control the diffusion and segregation, especially segregation for PNP type. So that's HBT. And really for HBTs, the leading player is really the European Union. And in the past 10 years, they have some collective efforts to work on this silicon germanium BiCMOS technology. And in the previous 2 projects, they actually had a .5 and .7 projects, and the current project is called a Taranto project, aiming to pursue silicon germanium HBTs offering Fmax above 600 gigahertz. So that's again, so this is a cross-section image of HBT, and then this one is the frequency versus a collector current, and here you show is about 600 gigahertz. So that's research effort in that aspect. So I view this as part of the beyond Moore's law efforts. Okay, so that's this one. And as I mentioned, my group has been studied this material system, starting from silicon germanium, and silicon germanium carbon, and pure germanium. Not pure to the sense that it's pure, but 100% nominal germanium. So one thing that we actually study is on the atomic level. We study the mass transport. So mass transport sounds more like a chemical engineering term, which means how materials, how material transport in the system, right? But here on atomic level, we're looking at how dopant diffusion happens, how dopant segregate, how interdiffusion between silicon and germanium happens. And with all this, for example, we have dopants, segregation with carbon. Carbon is a defect engineering element that changes the defect density. And strain has all impacts on all this mass transport and defects, germanium fraction, etc. So basically, this mass transport itself is a very complicated physical picture. That's why we have been studying it for more than 10 years with TI for TI's HBT. But of course, we have studied this topic for other CMOS and for silicon germanium with high germanium content. So that's on this mass transport, but today I'm not going to focus on the mass transport. I'm going to focus more on the photonic side. So this germanium on silicon laser, this topic is not a widely recognized topic yet. Okay, it had made headlines. Let me tell you a little bit of history on this topic. Really, why do we want to study germanium on silicon lasers, right? This actually started from how we feel like the current metal interconnects. For example, you see this, all these copper pads are becoming slower and consume more power when the technology, as the devices scale. So this interconnect bottleneck is one thing that can be addressed by optical links. So, for example, here, when we talk about how about we use optical link on chip? Here, really, it's on chip optical interconnect, because if chip to chip, right? So that's a different story. Because if we do chip to chip or board to board, we can always have, some other 3-5 materials that can be bonded or packaged together with the silicon IC. But now if we talk about on chip, so that's really the reason why we need to find a silicon compatible material for laser. And for example, here we see a on chip optical link. We need to have a laser for signals and modulated to modulated. And here we're showing some waveguides. And then here is the receiver side. We need a photodiode, etc., and circuits. So this idea was explored a lot at MIT for years. And again, this one is another case of a board-to-board optical link. I'll skip that. Really, talking about on-chip solutions, and there's two technology routes. 3-5 lasers, really 3-5 quantum dot lasers are mature, so they have really good performance, and they can be grown on silicon as quantum dots. But really the main problem is that materials, 3-5 quantum dots, they are grown in labs, but really making them to enter the silicon fabs is a huge deal. And it's very hard to enter the silicon fab. Whereas groups 4 lasers, for example, germanium lasers and germanium tin lasers, they have been demonstrated in the last 10 years. And people use stress engineering or doping to make germanium from indirect band gap to direct or pseudo-direct band gap material. So these materials are silicon compatible and can be processed with silicon, but we need to put lots of effort doing strain engineering or doping engineering. And for the case of germanium tin, we need to add tin in it. So they're still very early in research. And silicon, germanium, and tin, you can see they're all column 4 elements. So background, how do we engineer germanium to make it lace? So this was published 2007. So if we look at the band diagram, so here is a direct band gap. So it's 0.8. Indirect is 0.67. So they're not too far away. So about 130 millieV away. So if we add tensile strain, high tensile strain, that will make the direct and indirect much closer. And then we can dope this germanium. So we have N-type doping to provide free electrons that occupy the L band. Then when we do current injection, then electrons will split between this indirect and direct and indirect bands. And then we're going to have direct radiative recombination from the direct band. So that's not only an idea that has been demonstrated. The first electrically pumped germanium laser was demonstrated 2012, so by MIT researchers. And you see germanium is here, it's on silicon substrate, and germanium is undoped as promised. And this germanium layer is tensely strained because of the thermal expansion mismatch between germanium and silicon. So really, it's layers in this wavelength about 1.5 to 1.7 micron, that wavelength. And of course, if we make germanium into tiny bridge, and then we can have all this tensile strain to be concentrated. So that's a stress concentration method. And really, we can put huge uniaxial strain on it. And if that happens, we'll see the direct band gap, the black line. With tensile strain go up, the direct band gap keeps shrinking faster than the indirect. So at one point, germanium is going to become a truly direct band gap material. So that's with high uniaxial tensile. Biaxial tensile can also do the trick with less less strain, so about 2%, 2.5. Uniaxial, we need about 4.6%. Okay, so that's again stress engineering. And the second demonstration is from a German group. So doped germanium. So here is an N-type doped germanium, and the nucleation layer is on a silicon substrate. And lasing does happen. Of course, these initial studies show very poor germanium laser performance, but it's a 2 demonstrations so far. And this one is a germanium tin laser. So germanium tin laser has it's later than germanium laser, but the thing is that it's need really low temperature for it to laser. Whereas the germanium laser, they laser at room temperature. So that's an interesting story, and we have been following this for years. And our group also did some study on that. So photodetectors, if you can do strained germanium, you can also do strained germanium photodetector. Same thing apply, tensile strain, and then close the band gap. So therefore, germanium is become a more longer wavelength photodetector. So as a photodetector, yeah. So really, the progress of germanium lasers, 2 demonstrations, and the performance. If you see the performance table on the threshold current density, is pretty high. It's much higher than the commercial lasers, 3.5 lasers, and the efficiency is it's like at least 10 times lower. And wall plug efficiency is even lower. So basically not a good performance yet. So one of our efforts in study germanium lasers, unfortunately, we need really high quality germanium to make experimental germanium lasers. So our studies have been on the simulation modeling side, and we really want to analyze what's wrong with the first germanium lasers. So we proposed that we can do structure optimization and lifetime improvements. Really, this project is to use cross-light simulation tool to really debug the poor performance. And basically, we actually need to add germanium and strain-related band gap and material loss models into a commercial simulation tool called LastTip. And we need to validate our models with experimental data. And then from that, we can find out what if we do all these optimizations, for example, the cavity, cladding geometry, and we can also put in some better material parameter to see how much the germanium laser performance can be better. So that's the scope. So I'll skip some equations. You can read our papers if you're interested. Basically, we put in all these models, and here this structure is really a close match to the experimental MIT germanium laser structure. And our next point is, what if we optimize cavity structure and material data? So lots of optimization. And I'll skip some optimization curve you can find in our publications. Really, conclusion is that if we use thicker and wider germanium, that will increase the optical confinement. Thicker polysilicon, that will reduce the optical loss due to metal contacts. And really the key is to have better material quality that has longer minority carrier lifetime. And we can also use stress and doping engineering. So that was another publication related to that. So basically, if we use all these tricks, we can significantly reduce the threshold of lasing by about 100 times. And wall plug efficiency can be improved to about 15%. Here's another work is on stress engineering. So I'll skip all this content. The main idea is that if we add stressors, for example, we use a industry widely used silicon nitride stressors to introduce stress on the sides of germanium, on sides of germanium, for example, here, tensile silicon nitride, tensile silicon nitride, and we can also do some compressive stressor. If we do that, let me see. Yeah. Yeah, so if we do that, again, we'll see a big performance improvement, and the highest wall plug efficiency is over 40%. So basically, really, it's not the absolute number, it's to see how important and how much we can improve germanium lasers by using all this optimization method and better germanium material. So that's on the simulation projects we've done on germanium lasers. And that's our paper and sponsored NSERC and CrossLight. And then on the experimental side, we have some other projects. And this one is really talking about germanium here. You see, this is monolithic integration of VCSELs. VCSEL is a type of laser, vertical cavity surface emitting lasers on 100 silicon via germanium, a virtual germanium substrate. So let me show you. This one is a common industry VCSEL structure, and is built on bulk gallium arsenide substrate, and with hundreds of germanium aluminum arsenide as DBR materials, and we have a lasing gain layer. So really, motivation is to address the dramatic demand for VCSEL production. And VCSELs are used widely, for example, as infrared sources. So when we use cell phone, VCSEL arrays, they emit infrared light to shine on our face, and then the signal come back. That the signal comes back to calculate our face features and how distant we are from the cell phone. So also there's a 3D sensing, virtual reality, or auto navigation, etc., etc. So widely use of VCSELs. And so this shows VCSEL arrays, VCSEL illumination modules, and this is how VCSELs are used for face recognition. So basically, there's a strong demand on VCSEL production, about 6 times within a few years. So one thing, how do we enable mass production of these VCSEL lasers? One thing we looked at is to have silicon to be the substrate instead of the gallium arsenide substrate. And the reason is that really gallium arsenide are not good when scaled up. It's a very brittle material, whereas silicon is very robust. It can go to 12-inch, 18-inch. And germanium is lattice matched. So germanium is here as a transition layer, really to match to lattice match to gallium arsenide. So again, is when we change from 3-inch gallium arsenide wafer to 6-inch silicon, or nowadays from 6-inch gallium arsenide to 8-inch silicon or 12-inch silicon. That's a lot of process area available. Also, if we use silicon substrate, it's possible to integrate these light sources with all the CMOS. Yeah, VCSEL and CMOS integration. And potentially, so that's really just a potential. We can have all this transceiver, for example, transceiver light emitter and light detector on the same chip, same substrate. Really the difficulty, so here we actually see germanium lattice match, but difficulties on the thermal expansion and also on how to match the germanium lattice to gallium arsenide lattice anti-phase domain, for example. So let me see. Are we limited in time? So when should I finish? It's like 30 minutes,
You
right?
have, yeah, you have another 4 minutes.
Okay. Yeah, I'll skip some of the more technical details, but let me show you what we have. Also, one thing is that germanium epitaxy nowadays can be much better in quality with much less dislocation density here. So our previous efforts on that, we actually built a gallium arsenide based distributed Bragg reflector DBRs on virtual germanium on silicon 100 substrate. So if you see the stop band characteristic, which is a reflectance versus wavelength, you see how this germanium silicon based DBR really is almost on par with the bulk gallium arsenide based DBR. So that's very promising performance. And if you look at this TEM, silicon, germanium, gallium arsenide, and aluminum gallium arsenide DBRs, so really smooth and nice growth. And in recent progress, we actually already tried to grow the full VCSEL epi on silicon substrate. This goes from silicon, germanium, gallium arsenide, and full VCSEL. So we were able to, so of course, anti-phase domain is a main problem. So that's before growth, there are some anti-phase domain already. But after growth, we see really depends on the regions. We can have pretty smooth local, and this one shows pretty smooth local structures, and you see the periodicity has been very reasonable. But the main problem is the surface defects because the germanium is not 100% 100. There are some directions that grow faster, and so there's some fasting going on. So that's our first and second trials on growing full VCSELs. And besides from this, with germanium as an intermediate or transition layer, we have a recent breakthroughs by IQE, it's a UK company, where they just use the bulk germanium because really silicon add another layer of difficulty because silicon substrate has a different thermal expansion coefficient, whereas germanium and gallium arsenide match very well. So they use the germanium, and germanium you can do 8-inch and even 12-inch germanium wafers. And germanium, here we're talking about bulk germanium. It's very, very low in defect density. And if I show you the comparison between germanium-based VCSEL and gallium arsenide-based VCSELs, really it's on par. And especially this process has not been fully optimized for germanium. So that's very encouraging. So again, that's IQE's. So I call this IQE's work. They just released that last year. So to summarize, so today, since we talk about the beyond the more, I really focus on my efforts on materials and processing innovations. The first thing I talk about is silicon germanium HBTs. They are really key devices for 5G, 6G, and beyond that. And I didn't spend too much, but you can go to my website and look up our papers. For germanium on silicon lasers, they're relatively new in research, and they can be improved and optimized and through better germanium quality and stress engineering. For VCSELs on bulk silicon or on bulk germanium substrates, we have demonstrated on par performance DBRs on this ART aspect ratio trapping germanium on silicon. And the first full VCSELs has okay uniformity only locally, but there's some surface problems. And on the bulk germanium substrate, VCSELs are successfully demonstrated to be on bulk germanium substrate by IQE. So with this, that's the last slide, and thank you so much.
Thank you very much, Professor Schaaf. We don't have any questions, but maybe I'll ask one. I think there was in a recent Nature article, there was a demonstration of a 4-qubit quantum processor based on germanium whole spin quantum dots.
Oh.
And I'm wondering whether, whether you see that as being one of the advantages that integration on silicon, thinking about quantum qubits using germanium rather than other semiconductors.
Yeah. So first of all, I didn't have a chance to read that article, but I can comment in general. So in general, germanium is pretty good to be grown on silicon very well. Really depends on the processing temperature. If germanium is on silicon with pretty low processing temperature, say below 700, then I expect that we don't have lot of silicon germanium interdiffusion. So really with the higher processing temperature, interdiffusion happens, and interdiffusion really makes germanium silicon to have a sloped interface. You'll go from germanium to a mixture of silicon germanium, that's a transition region of silicon germanium, and then to silicon. So originally you want to do quantum confinement, for example, you want germanium and silicon to have a sharp interface. But if interdiffusion happens, especially with higher temperature, that quantum confinement can be easily smeared out. So really, I'd say processing it's one of the great concern. So really depends on how this quantum bit is integrated. And for example, if that need to have another, silicon IC, for example, to control that or to be the input and output, whatever. So it can cause some integration issues, but I don't think it's it's a showstopper. So basically, if we do all the fabrication like high temperature steps before germanium is deposited, and keep low temperature after germanium is deposited, and that's in terms of processing, that's very doable.
Mm-hmm.
Yeah.
Thank you.
So that's just my comment on processing. So have to see the paper to tell you more. Yeah.
Okay. Thank you very much. So thank you, Professor Schaaf, and I want to thank all of our speakers for giving their precious time to us today and share their knowledge. And I want to thank as well our partners in this webinar, Huawei. Please look at the nanocanada.com website, because we have an exciting event coming up on October 21st, which is basically a launch event for our first international conference in June 2020. And you'll see that the themes will capture your imagination, but it's all about advanced materials and nanotechnology in various fields like healthcare, addressing sustainability issues, but also space and beyond. So it's a rendezvous for June 2022. And if you wanted to have a taste of it, then please register for October 21st event. So thank you again to our speakers and to the audience for joining us today. Merci.
Yeah. Thank you.
Thank you.